Okay, so we are working our way through periodic trends. We started last class with atomic and ionic radii, which has to do with the size of our atoms and our ions. And we talked about how the size is determined by some of those things, those core things we talked about the previous class, which are sort of the energy, the number of energy levels they have, the amount of shielding, because the more energy levels you have, the more shielding that you have for your valence electrons, and then also the nuclear charge. And so usually going down a group, the thing that affects it is the energy levels and the shielding, because as you go down, you're adding more energy levels, which increases shielding. And as you go across a period, usually what causes it to have a certain trend is the nuclear charge, because as you go across, you're not adding energy levels, you're just adding electrons on the same energy level, that valence shell, and you're adding protons in the nucleus that will pull that valence shell in closer. And so those things are going to directly relate to the three trends we're going to talk about today. And so I'm going to switch over to the iPad because we're going to talk about ionization energy, electronegativity, and electron affinity today. So they're all really long names and they sound similar, like electronegativity and electron affinity, but they actually are different things. So we're going to see their definitions, and then we're going to talk about how the trend works going across a period and down a group, just like we did with atomic and ionic radius. All right, here we go. All right, so one thing I want to point out first, IB is International Baccalaureate. So a lot of times, because it is international, you'll see weird spellings. Like here, like if you notice on Canvas, I spelled it with a Z, ionization energy. That's because I'm from the United States and we usually use Z's. In like Britain or in Europe, a lot of times they'll use S's in words, like they do the same thing for F and pH. Like on the periodic table, we have sulfur with an F, but you'll see a lot of times in things from Europe, it'll have a pH instead of an F. Okay, so those minor spelling things, that's just sort of a language cultural type of thing. So ionization, you can do with a Z or an S either way. I would say do the Z because that's really the kind of the American spelling. Okay, but it's not a typo. It is the same thing. It's just another way of writing it. Okay. All right. So ionization energy, the definition, we need to know this definition. Okay. It's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So there are some key terms in here. I will tell you, this has shown up on an IB test. There's been like an open-ended question on paper 2 that has said, define ionization energy or first ionization energy. And so the key things is obviously it's the energy required, but you have to have that it's to remove 1 mole. So you have to have the 1 mole of electrons. You can't just say to remove electrons. And then it has to be from 1 mole, and you have to have gaseous atoms. You can't just say from 1 mole of an element or 1 mole of atoms. You have to have that gaseous words because that's telling us it has to be in the state of being a gas for this to occur. Okay. So the definition is very specific, and you do need to make sure that you include all of those words in the definition. You can't really paraphrase it or anything like that. Okay. If you're asked to represent the ionization energy like in an equation form or in a reaction form, this is what it would look like. Okay. Oh, I meant to do the highlighter. Switch over. Okay. So it would look like this equation right here. So X in this example, that's just representing an element. Okay. So if I wanted to do sodium, okay, I could do Na, and it's going to be in the gas form. And then it would form a sodium ion, which is going to be Na+1, still in the gas form. And then I have an electron. So E-, that's the symbol for electron. So the first ionization energy, it's going to lose 1 electron. Okay, so sodium, because it's an alkali metal, its first ionization energy, that's pretty much the only one it has because it only has 1 valence electron. If we want sodium to lose a second electron, it's pretty much impossible to do because you'd have to take that second electron from its now full outer valence shell And that would require way too much energy that it's not really possible, okay? Now, some elements though, elements that like the alkaline earth metals, like if I were to do magnesium, let me clear some space up here. Let's say I want to do magnesium, and if I'm asked to do the first ionization energy, I'm just removing 1 mole of electrons, okay, just 1. So I would have like magnesium, it's in the gas form, and then over here I now have Mg, still the gas form, it's got a +1 charge, and then I removed that 1 mole of electrons, okay? So that's the first ionization energy. What if I'm asked to do, because magnesium is an alkaline earth metal, so normally when it loses electrons, it loses 2, not just 1. And so what you might not be asked to do is you might also be asked to do the second ionization energy. And the second ionization energy for an element like magnesium that's in group 2 that can lose that second one really easily, you would start now with magnesium, the gas form, but now you're going to start with that magnesium ion that has the +1 charge, because this is the second time it's going to lose an electron. And so this thing looks the same, except now over here, now the magnesium is going to be that true magnesium ion with the +2 charge, and it's now lost a second electron, or a second mole of electrons, I should say. So just be aware that like your alkaline metals, they typically only have that first ionization energy because they only lose 1 valence electron easily. Your alkaline earth metals, they can have a first and a second ionization energy. And then aluminum is pretty much the only metal it can have a third ionization energy because it has that +3 charge. And then some of our transition metals, obviously, they can have multiples because they have multiple charges as well. But most of the time, we're just going to see first ionization energy and then maybe the second one for some of our alkaline earth metals, okay? The next bullet here, it just says what they're measuring, okay? They're a measure of the attraction between the nucleus and the outermost or the valence electrons. So this directly relates back to our other trends, to the size, to the atomic radius, and also to the nuclear charge and the shielding, okay? Because if first ionization energy, excuse me, guys, choking on myself, is the amount of energy required to remove 1 mole of electrons from 1 mole of gaseous atoms, then that means that if I have an atom that has a stronger attraction to its valence electrons, I'm going to have to put a lot more energy in order to take that electron away, okay? If I'm talking about an atom where the attraction between the nucleus and the valence electrons is weaker, it's not as strong, then it's going to require less energy. I'm going to be able to take it a lot easier. So how that correlates to our size is, if you remember where the atoms get smaller and larger in terms of atomic radius, then all you have to remember is that smaller atoms means more attraction, which means higher ionization energies, okay? Larger atoms means weaker attraction, which means lower ionization energies, okay? And so if you look at an actual periodic table, what you're going to see for ionization energy is that as you go across a group left to right, ionization energy is going to increase. And the reason it increases is because as we go across, our atoms, our atomic radius is getting smaller because the nuclear charge is increasing. So like I said, it all ties back together. Nuclear charge is increasing because we're adding more protons. That causes the atom to get smaller and shrink in because there's a higher attraction to the valence electrons. And when there's a higher attraction, that means that it requires more energy in order to try to remove one of those valence electrons, okay, or 1 mole of them. As you go down a group, what do we think is going to happen here? We think it's going to increase or decrease as we go down a group. Think about the size of the atoms. Which one did you say? Yes. So it's going to, and I'm going to turn sideways so I can write this. So as you go down, it decreases. And the reason is, again, thinking back to the size, as we go down, we're adding more energy levels and increasing the shielding. So that causes the atoms to get larger because there's less attraction from the nucleus to the valence electrons. So larger atoms, less attraction, that means the ionization energy is going to get lower as you go down, okay? So that's the basic trend for going across a period and down a group. Now, the other thing with ionization energy that we have to kind of be aware of is this graph. They like to show this graph. And usually this goes up to element 20, calcium, because after calcium is where all of our transition metals come in, and then that's where things kind of get wonky. So they will show you graphs like this, where down on the x-axis, we have the atomic number. So that's the number of protons, also like our nuclear charge, okay? And then here on the y-axis is our ionization energy, and it's measured in kilojoules per mole, okay? Kilojoules is energy, and it's per mole because of our definition saying that it's for 1 mole of electrons, okay? So what happens is, these are in order, numbers 1 through 20, but I can start to see some patterns here. If I look, here's hydrogen and here's helium. So that is period 1. So hydrogen's lower, helium's higher, okay? That makes sense because we said it's going to increase going across. If I then go to the next ones, which would be period 2, so period 2 starts with lithium, it ends with neon, okay? So the general trend is that, yes, it's increasing. I can see that's going up, right? But here in the middle, there's some weirdness going on because they're not all going straight up. There's some where there's kind of a drop between like beryllium and boron and between nitrogen and oxygen. And so we're going to talk about why that is, because there's a reason, there's an explanation for that. But in general, as I go across the whole period from lithium to neon, it increases. And then when I go back to the third period, I kind of start back down here again because I'm back with my alkali metals in group 1. And if I go all the way up to argon, I see the same thing. It's in general, it's increasing. But again, I still see these kind of weird drops. And the drops, if you notice, they're between the same groups, okay? And so then we have potassium and calcium that are in the 4th period. So that's kind of looking at it from the period point of view. Now, if I want to look at it in terms of groups, okay, let me erase my circles. So for groups, okay, group 1 is like hydrogen, and that's our alkali metals. So hydrogen is in group 1, lithium is in group 1, sodium's in group 1, and potassium's in group 1. So you can see, obviously hydrogen's not an alkali metal like lithium and sodium and potassium are, but I can see in general, it's decreasing as I go down that group. As I go from lithium to sodium to potassium, it's getting a little bit lower. It's not as big of a jump as like from lithium up to neon on that period. But as I go down from lithium to sodium to potassium, down the alkali metals, it is decreasing, okay? If I look at my group 2, so I have beryllium, magnesium, and calcium. They are also decreasing as I go across, okay? So as I read this graph across, looking at group 2, which is beryllium, magnesium, calcium, those go down the group and they are getting smaller, or it's getting lower, sorry, not smaller. And then I can look at group 3, boron, aluminum. Okay, there's not really a third one to compare. Group 4, carbon and silicon. Let's see, group 5 is nitrogen and phosphorus. Gotta find a different color. Group 6 is oxygen and sulfur. Group 7 is fluorine and chlorine. And then my noble gases are always the last one. So we have helium, neon, and argon. So what I kind of did here is I just tried to kind of highlight them in different colors so that you can see like all the yellow ones, those are in the same group. They're in the same family. The 2 light green ones, boron and aluminum, they're together. The orange ones are together, the blue, the purple, the red, the pink, and then the dark green. So it might help you to do something similar, to like label it or color code it in some way so that you can tell where on this graph are periods and where are groups. Okay, the periods are easy to see because like it just goes lithium all the way up to neon and then sodium all the way up to argon. So the periods are a little easier to see. The groups are what are harder to see if you don't have some sort of color coding or labeling going on. And so what we see is we see those trends proved. We see that the periods are increasing. We see that the groups are decreasing, okay? And then what we want to talk about is these exceptions. And so here's kind of the summary of the general trends. And so it says that it decreases down a group, it increases across a period, just like we talked about. And for the explanations are what we talked about. So The number of occupied energy levels increases. And then that means valence electrons are further from the nucleus, which results in a weaker attraction. Okay, so that requires less energy because there's a weaker attraction because they're further from the nucleus. The other explanation is that there's increased shielding, and that also reduces that attraction. So more energy levels and increased shielding both cause the attraction to be weaker, and therefore it requires less energy as you go down a group. As you go across a period, we talked about nuclear charge. So nuclear charge increases, and so that means that that attraction between the nucleus and the valence electrons increases, which means that it's going to require more energy for you to overcome that attraction and take an electron away. Okay. They also relate it back, like I said, to atomic radius, because atomic radius decreases. The valence electrons are closer to the nucleus, so there's a stronger attraction. Okay. So that basically is just summarizing what I kind of said and went over. Here are the exceptions. Okay, we're going to talk about the exceptions. So one of the exceptions is between groups 2 and 3. Okay, this is beryllium and magnesium are in group 2, and boron and aluminum are in group 3. So why is there a dip? Why does it go down between those two? Because we're like, well, if it should keep going up across the period, why doesn't it just keep going up in a straight line? The reason has to do with our sublevels. If we look at the electron configurations for beryllium and boron here, beryllium is 1s2, 2s2. When you get to boron, your next electron, it goes in the 2p sublevel. And so the reason that boron and aluminum are lower is because this next bullet, it says electrons in the p orbitals, they're of a higher energy. And so they're further from the nucleus than the s orbitals. And so since they're further away from the nucleus because the p orbitals are further than s, that requires less energy to remove. So that's why there's a slight dip, because that electron that goes on for boron and for aluminum, it's going into the p sublevel or the p orbital, which is higher energy, and it's further from the nucleus. And since it's further from the nucleus, that means it requires less energy to remove, and we see a dip in the amount of energy that's required. So the same thing explains magnesium and aluminum over here. It's the same reason. The only difference is magnesium would be 3s2 and aluminum would be 3p1, kind of like it says right here. Okay. But that's the reason, is because the p orbitals or the p orbitals have higher energy, so they're further from the nucleus. Similar explanation for the next one. The other exception, it's between groups 5 and 6. So nitrogen and phosphorus are in group 5. Oxygen and sulfur are in group 6. So we see another dip here. It's a similar explanation, but instead of going from an s orbital to a p orbital, it's not changing orbitals. It's the location within the p orbital. Okay. So if we looked at like the orbital diagram for nitrogen and oxygen, okay? So nitrogen and oxygen both end in 2p. So if I wanted to label, these are like the 2p sublevels. And so nitrogen ends with 2p3. So its orbital diagram is drawn like this. Each p orbital has one up arrow, okay? Because we have to do the Hund's rule, where we give each orbital one electron before we start pairing them up. Now, when oxygen comes in, oxygen's got one more electron. Well, that electron that oxygen has goes up and it pairs up with the first electron that's in the first orbital. And so what it says right here is, it says for oxygen, the electron that they're taking away, so the first electron that's taken, if you try to make oxygen an ion, it's this one right here. It's that second one. Let me redo that. So because it's that second one, it's coming from what we call a doubly occupied p orbital. And so if you have an electron in an orbital that's already got another one, it's doubly occupied, it's going to be repelled by that other electron. And because it's being repelled, it requires less energy. So if it's in one of these other ones, like, you know, this one right here is only half filled. So there's nothing in there repelling it. It's just that one electron. So that's going to require more energy to remove. Rather than this other one, this second, the one that's paired up for oxygen, the other electron that's paired up with it, it's repelling it. So it's almost like, it's like trying to push it out. And so it doesn't require much energy for you to actually be able to remove it. Okay. And so both of those exceptions have to do with our sublevels and our orbitals, with our electron configurations. It's just that the first one had to do with changing from like an s to a p orbital. This one has to do with a p orbital being half full versus totally full, or the doubly occupied. All right, so there's practice questions after that. I'm going to go ahead and go down here so we can do our other two trends. So our other two we're going to talk about today, electronegativity, okay? Electronegativity, this one determines what kind of bonds we make, okay? So electronegativity, it's a measure of the ability of an atom to attract a bonding pair of electrons. So the higher an electronegativity, the more likely an atom is to take an electron from another atom, basically, okay? And so it's measured on this scale. It's called the Pauling scale. And so the values for electronegativity, the highest value is 4. The lowest value is 0.7. And so fluorine, all the way over here, fluorine is the most electronegative element. Francium is the least electronegative element down here. And so the trend, you can probably predict the trend, because if I tell you the highest one's up here with fluorine, then that tells me that as I go left to right, it increases. Okay, fluorine is the highest, so all the way on the right side are where my high ones are. As I go down the group, it decreases. I'm just going to write a D. Y'all can fill in decreases, because francium is the lowest one. Okay, they are in your data booklet, and I think the ionization energies are too. So all of these things that we're talking about, all these trends, if you ever need to refer and look up numbers, look up values for them, they are all in your data booklet. Okay, this one's in section 8. It has this exact image of this periodic table. And what it does is it has the number up here. I believe this number is the ionization energy. And then, actually, no. Yeah, that's right. I think that's the first ionization energy. Oh, yeah. I should look. There's a key up here. It would help if I would read stuff, you guys. Okay, so the first ionization energy, the bottom number here, that's the electronegativity. And then up in the top corner is the other one we're going to talk about today, the electron affinity. Okay. And so what you need to know, electronegativity, if you notice, the noble gases don't really have electronegativities because they don't form bonds. Okay. The only one that does have one is xenon, because when we get to bonding, we're going to learn that some noble gases can make bonds, like xenon, and krypton can sometimes. And it's because they have the weird like D block electrons. Okay. So that's the general trend for electronegativity, and that's kind of what it summarizes here in these two bullets underneath. Okay. The reason that it's increasing or decreasing, so it increases from left to right across a period for two reasons: increase in nuclear charge and decrease in atomic radius. So like I told y'all, it all goes back to that. Because if an element or an atom, if it has a small radius, because its nuclear charge is so strong that it's holding all of its valence electrons really close, then not only is it going to hold its own electrons very close, but it's also going to be able to attract other atoms' electrons more easily. Okay. And so higher electronegativity means you're more likely to like take electrons from another atom. Okay. And so smaller atoms are going to have higher electronegativities because their nuclear charge and their smaller size allow their nucleus to attract electrons from other atoms more easily. Down a group, it's the opposite. We talked about that it decreases down a group because the atomic radius is increasing because we're adding more energy levels. And so as you add more energy levels and there's more shielding and it increases your size, that means that the nucleus is going to be really far away from the valence shell. So it not only is it going to have a hard time holding onto its own electrons because it's going to have a very low ionization energy, it's going to have a very low electronegativity, because if it can't even hold on to its own electrons very well, it's definitely not going to be able to attract bonding electrons as strongly. Okay. You have a few questions on that. They're fairly easy, fairly straightforward. The last one, electron affinity. Electron affinity, we'll highlight our definition here again. The energy released when 1 mole of electrons is added to 1 mole of gaseous atoms to form 1 mole of negative ions. So this is like the opposite of ionization energy. Ionization energy, it was the energy required to remove an electron. This one is the energy released when you add an electron or 1 mole of electrons. Okay. So notice they still say similar things like 1 mole of electrons, 1 mole of gaseous atoms. So some of the terms are similar, but they're just the opposite. So notice on this one, we have kind of that same setup where we have kind of a generic element symbol with the gas form, but now the electron's on the reactant side because it's being added. And so over here, I end up with a negative ion, okay? I can also, just like with ionization energy, I can have a first and a second ionization energy. I can have a first and a second electron affinity, and it kind of works the same way. I just take the ion that I made on the first one with a -1, and I'm going to add another electron to it and make it have a -2 charge, okay? So what you're going to find is that the trend for this one, it also decreases down a group, okay? So that's what it says here. Let me get my highlighter back. The increased nuclear charge down a group, it's offset by electron shielding. So the fact that you have more shielding and your nucleus is further away from the outer energy level, again, your attraction is less, and so you release less energy when you add an electron, okay? They don't really have the trend for going across the period here because it kind of varies. It actually, it's not that it doesn't happen, it's just that it doesn't, doesn't follow a pattern as well as some of the other ones do. But down a group, we definitely need to know that it is decreasing. So like if I look here, I'm releasing 73, but all the way down here, I'm only releasing 46. So the negative signs on these, the negative sign just means that the energy is being released, okay? And when we get to like topic 5, we learn more about that because we learn about endo and exothermic reactions. But anytime energy is released, your energy value is going to be negative because the negative sign indicates it's being released. So it decreases going down a group. If you look at some of the ones where it's going across, like for example, sodium is -53. Magnesium doesn't really have one. But then over here we have -42, -134, -72, -200. So this is why we don't really talk about it going across because it doesn't really follow a great pattern. It does in general increase. The amount of energy is going to increase in general, but it doesn't follow as good of a pattern as the other trends do. So if you want to say that it increases going across a period, you can say that. Just be aware that like there are a lot more like dips than in the other ones, okay? And then there are some elements that like don't even have one, like beryllium, magnesium, nitrogen, they're all kind of blank, okay? And so that's why we only really focus on the group aspect of this one. So then there's a few more exercises, and then that's where we're stopping for today because we're going to wait to get into melting point next week.